when it comes to LTE, you may have seen in a marketing clip or read somewhere that LTE can achieve up to 300 Mbps. Or you may have heard that with 4x4 MIMO or with 8x8 MIMO it can achieve even more than that. What did I just said? I said with 4x4 MIMO or 8x8 MIMO or even with 2x2 MIMO. And that's what we are going to discuss in this specific video about multiple input, multiple output antenna schemes. Now, there are some core concepts which we need to understand about MIMO, and once we are clear on those core concepts, rest of the discussion will become pretty smooth. So what I'm going to do, I'm going to discuss three schemes for multiple antenna schemes, three schemes about multiple antenna schemes, and then after that we will look and learn about certain definitions related to MIMO, and then we will see what does it say and how different coding, precoding, and closed loop spatial multiplexing, open loop spatial multiplexing, and other different schemes work. So with that being said, let's get started with MIMO scenario. Now, before we go and start drawing something on the screen, one thing we need to understand and make ourselves clear is MIMO not always means that it is about increasing throughput. Multi-antenna schemes can mean differently in different contexts. You can use multiple antenna schemes just to reduce fading and improve the reliability of throughput. You can also use MIMO schemes or multi-antenna schemes in order to focus on a certain user using beamforming. Or you can use different streams or different streams of data for different users using spatial multiplexing schemes. So there are different schemes which we are going to talk about and then see how each one of them works. Let's get started first of all with a simple scenario of wireless medium. So if we start with the simple scenario of wireless medium, let's say if we have a transmitter here on the left side and we have a receiver on the right side, and let's say you are transmitting something. The only thing which can be problematic over here between the wireless medium is actually the wireless channel or the wireless medium, because we do not know, it's unpredictable. Unless we know the channel information, we can massage our signal already so that it can be received by the receiving entity in the same way we want it to be transmitted. But since we have a wireless channel in between, and that is the reason we need to come up with different schemes in order to protect the signal. So this is wireless channel. So let's say if because of this wireless channel there is a lot of fading and whatever we are transmitting, it is not being received reliably at the receiving end or receiver is on the right side. So what we can do, we can use one of the scheme which we call as transmit diversity in order to improve the reliability of coverage. And in this case, let's say we have wireless channel and a lot of fading over here in the wireless channel. One way to do this is, let's say on the transmitting end we have two antennas, right? And what we can do is, in those two antennas we can transmit the same information, but before we transmit the same information we can introduce certain delay. So let's say we are transmitting information S on the transmitting end, and on the receiving end we are receiving that information. In order to improve reliability of the transmission, what we will do is we will transmit same information S at time t1, and since we have introduced a delay on the other antenna, at a different time, let's say time t2, we will transmit the same information. So the receiver, what it will do, it will get two versions of the same information. One version will be at time t1, the other version will be at time t2. So depending on whichever version is the corrected version, or if two different versions are the same but they have a different coding rate, and these are different redundancy versions, using circular buffer matching, the receiving end can receive the actual information which was being transmitted. So the idea here is, as I mentioned earlier, with different antenna schemes we can use it differently. In this specific example, what I just did in front of you, that was an example of transmit diversity specifically focused on reducing fading. So that's one of the scenario or schemes for multiple antenna schemes, right? Let's take another example. Before I go to the other example, let me label it here. So this is an example of transmit diversity. We will talk more about this later on. Transmit diversity. Okay, let's talk about another scenario here, and this time let me remove this one first. And in this case, the scenario will be about improving throughput. Or before we talk about improving throughput, let's draw a simple scenario. In this case, you have a coverage of a cell and you have a number of users. One user, James, is standing at the edge of the cell. Another user, John, is standing in the middle of the cell. And then we have another user, Adam, standing over here. So in this case, let's say, so for the case of beamforming, let's take an example. We have 3 users, and in this case, these 3 users, including John, James, and Adam, and let's say the transmitting antenna on the base station has 2 transmitting antennas in this case. Using beamforming, what can happen is we can focus the streams to one of the user. Let's say if the antenna wants to focus, or E node B wants to focus all the streams or mainstream towards this user John, that can be possible using beamforming as well. Of course, there are different mechanisms behind it, but the concept of beamforming is you can unify the transmission towards a certain user using beamforming wherever he or she may be. And we will talk about this beamforming further on. Then another concept which we need to get our heads around is about precoding. But before we talk about precoding, let's go and talk about spatial multiplexing. So in case of spatial multiplexing, the idea is simple. Let's say if you have 2 antennas at the transmitting end, this is the transmission side and this is the receiving side. In this case, rather than transmitting just one stream of information, 2 streams of information can be transmitted. So in the same amount of time, the user can receive twice the same amount of information using 2 antennas. So there will be 2 streams of information going, and if the receiving end has 2 receiving antennas, it can receive 2 streams of information using the same amount or in the same amount of time. And that's the idea of spatial multiplexing, which is used to improve the throughput or increase the throughput in this case. Now, having said that, let's go and talk about precoding before we go further with this discussion. And the idea of precoding is simple. Let me erase this first before we talk about precoding. So let's assume we have a channel, a wireless channel over here, and we have 2 antennas. We have a transmitting antenna and then we have a receiving antenna over here. And let's say the wireless channel at this moment, when we are doing transmission, let's say there are 2 antennas, or let's say for the sake of simplicity, an example, let's say the wireless channel is behaving in such a way that it is giving 180-degree phase shift to whatever we are transmitting. So let's say at the transmitting end, if the information is, let's say if we are transmitting a number 2, just for the example's sake, at a very simplistic level, if we are transmitting an information S equals to 2 and the wireless channel is giving 180-degree phase shift, what does that means is that at the receiving end, what you will receive rather than receiving 2, the receiver is receiving -2. So whatever you're transmitting, that gets phase shifted 180-degree, and that's what is being received. If we know the channel conditions already well in advance, meaning if we know that the wireless channel in between is giving 180-degree phase shift, we can massage or prepare our transmitting signal already well in advance so that it can overcome this 180-degree phase shift. So what we will do instead over here is we are going to make the signal in such a way that it will be multiplied. So we can do something like this. We can multiply the signal which is being transmitted with an input, and in this case the input is let's say I multiply it with the weight, and in this case the input is just 180-degree phase shift already, which is being shifted by pi, or 180-degree phase shift is already being given here. Now in this case, even though we are originally transmitting number 2, however with a 180-degree phase shift, at the transmitting end it will be changed, and what actually will be transmitted will be -2. Now we know the wireless channel is already giving a 180-degree phase shift because the way it's behaving. So at the receiving end, what you are going to get, at the receiving end you are going to get +2 instead. So originally we wanted to transmit 2, and by adding an extra weight, which is a 180-degree phase shift already to the transmission, we have been able to achieve what we wanted to transmit originally in the first place. So this weight over here is actually the weight which we need to use when we know the channel conditions already. And this whole simple example which I gave you, this example is the concept of precoding. This example is a simplistic concept of precoding. So let me write it over here, precoding. And there is a matrix which is used to find these weights, which can be used to improve the channel coverage, and that matrix is called as precoding matrix indicator. We will talk about that later in the slides, but this is the idea of precoding, and the weight which is used from a matrix that's called as precoding matrix indicator, abbreviated as PMI. So if you know the channel conditions already, you can already specify a weight from the code book, and then using that particular PMI value you can overcome or massage the signal so that it can overcome the channel impairments. So that's the idea of precoding matrix indicator, or the precoding process in general. Having said that, we are going to see in the couple of slides coming further down how this precoding is used. And the concept of precoding matrix indicator is, let's say, elaborated once again. Let's say if I have an already considered table which has a number of weights. This is weight W1, this is W12, this is W21, and this is W22. So let's say during transmission, I know how my channel condition looks like. So if I know the channel condition already, I can pick any specific weight and multiply my input or change my input with that specific weight from this matrix. Then it will be called as precoding matrix indicator. So just a revision of what we learned just now. So that's the idea. Keep this concept in mind while we go further on. Then there is another concept which is termed as rank indicator or layers. What is a rank indicator? So in order to have the concept of rank indicator, let's say we have a site here, and this site has 2 antennas for transmitting. So let's say this site has 2 antennas for transmitting, and then we have a user over here, and this user has 2 receivers. UE has 2 antennas for receiving. So the transmitting side can transmit 2 streams of information, receiver can receive 2 streams of information. Now here is the specific thing or concept we need to get our heads around. Let's say this is the coverage area, okay, the one which I have drawn. This is the coverage area, and if the user, in this case let's call this user as Sunil is the user in this case. So if the user is standing at the edge of the cell, then obviously the user is in bad RF coverage. So keep this thing in mind. In bad RF coverage, UE is not able to receive high streams of information or data, meaning it cannot receive high amount of data because RF coverage is bad. If it tries to receive it, the data will get corrupted, user will not be happy, E node B will not be happy. So at this point, even though the number of receiving antennas is 2, but then the UE will keep on sending a will keep on reporting back to the E node B, telling the E node B that at this moment my rank indicator is 1. Now what does it mean my rank indicator is 1? Meaning that UE is telling the E node B, if you have to send streams of information to me at this point, do not send me more than 1 layer of information or 1 stream of information, because I am not in good RF coverage at this point. Though CQI value is another one which is used to send the measurement, which is used to send the channel conditions where user is standing, but rank indicator is specifically in terms of MIMO scenario. And in this case, E node B, once it will get this information, it is not going to transmit information on two streams of information after getting rank indicator value equals to 1. So if that's the case, let's say the same user now moves closer to the cell, and in this case it comes somewhere over here, and now it is standing in rather better coverage. At this point, the UE will start transmitting a rank indicator value equals to 2. What does this mean here? In this case, by sending a rank indicator value equals to 2, the UE is trying to convey this message to the E node B. Now I am in good coverage. If you want to transmit two streams of information to me, I am ready to receive it. Keep this thing in mind. UE keeps on sending rank indicator values to the E node B. It's up to the E node B to make a decision either to send on two streams of information or one stream of information. But the idea here is that UE is always telling the E node B wherever it's standing and how many streams of information it is ready to receive. Okay, so that's the concept of rank indicator. In this case, it is different than the CQI value, channel quality indicator, which you know about LTE, or you may have heard about LTE. So that's the idea. We are going to revisit this rank indicator once again. For those of you who are not aware of channel quality indicator, before I go into closed loop spatial multiplexing, it's important that I go through the CQI concept as well here. So let me go through CQI concept specifically. So in case of CQI, what happens is when a UE is standing or connected to the cell, and let me give the title this time, we are going to talk about CQI value. CQI stands for channel quality indication, and it ranges between 1 to 15. 1 means worst, 15 means best. So as we learned previously, in case of, let me make some changes, erase certain things. As we learned, UE keeps on measuring reference signals when it is connected to an E node B, and based on measuring those reference signals, it realizes what type of coverage the user is in. And based on that coverage, it decides if a reference signal received power value is good, it will map that RSRP measurement into SINR, and that SINR value is translated into any of this range between 1 to 15. So if user is standing away from the cell edge, the user is going to report a CQI value which is not good. Let's say if this user Sunil is standing over here, the UE is going to report a CQI value, let's say equals to 4. Now why a value of CQI 4? Because CQI value 4 is not the best, it's not the worst, the user is not at the edge of the cell. And once E node B will receive the CQI value 4, E node B is going to make a decision what type of modulation scheme needs to be used by this specific, what type of modulation scheme needs to be used for this specific user. Similarly, if a user is standing over here, and let's call this user as Girish, let's just say as an example, and in this case the UE is going to report a CQI value of, let's say, 13. Why? Because this user is standing way closer to the cell edge. When E node B is going to receive a CQI value of 13, then E node B is going to make a decision, okay, I can give 64 modulation scheme for this user. So this user will start getting higher data rate throughput on a different modulation scheme, while in this case the other user is going to get data rate at QPSK modulation scheme, which will be slow speed data or low throughput data. So CQI value is reported periodically, it can be reported aperiodically as well. But even though if MIMO is being used or not, as we know, CQI value is being reported all the time, if in case of MIMO or without MIMO scenario. But the reason to have this understanding or review was, before we go into closed loop spatial multiplexing and open loop spatial multiplexing, it's important to have that idea in mind. Now we have the basis to go further, so let's go and talk about closed loop spatial multiplexing. So folks, we learned about spatial multiplexing already. It's the scenario where E node B is using more than one streams of information. Let's go further and talk about what is closed loop spatial multiplexing, and let's consider it with an example. So let's say this is a site and this is the coverage, and this is a user here. Let's say this is another user. As the name indicates, spatial multiplexing, so in this case there are more streams of information more than one stream or layer of information which the eNodeB is going to transmit, and UE is also having more than one transmitting and receiving antennas. So in this case eNodeB is going to transmit, let's say, 2 streams of information. It does not mean if closed loop spatial multiplexing is used always there will be more than one stream of information, but the idea is in this case of closed loop spatial multiplexing, when the transmission will be received by the UE is going to report 3 types of information in return. What are those 3 types of information will be received by the eNodeB from UE? One is CQI value, the other one is rank indicator, RI, and then the third one is PMI. We talked about CQI. CQI is just measurement of channel quality indication. Rank indicator is indication telling the eNodeB either UE wants to receive 1 stream of information or 2 streams of information, or whatever number of antennas and layers there exist, while PMI is the actual value which UE thinks should be used by the eNodeB to send data towards me. Now keep this thing in mind, PMI value means that UE is going through the computations of its own or on its own and sending a recommended value to the eNodeB that it should use this particular PMI value or precoding matrix indicator value in order to send data to the UE. Now if eNodeB uses that value or not, that's another story. It's up to eNodeB to accept or deny that particular measurement, but the only difference here is in addition to CQ and rank indicator, UE is also going to propose a specific PMI value. Now get this understanding from this perspective. UE is the one which is receiving signal in the downlink side, so UE also have an idea based on measuring reference signals that what the channel condition looks like from the UE perspective. So based on those particular channel measurements, UE is going to propose after computation a PMI value, and then it is going to send that to the eNodeB. And that's the whole idea about with the title closed loop, because in this case the loop is closed when eNodeB is sending data and UE is proposing a return with these 3 measurements. So that's the whole idea. Now what are the practicalities of closed loop spatial multiplexing? Since in this case UE has to compute PMI value, which may take time for you to do measurements and propose a precoding matrix indicator. So that's why closed loop spatial multiplexing is not recommended for high mobility scenarios, because UE will have to go through a certain time to compute what PMI value should be used by the eNodeB. So this is used in case of low mobility or slow mobility scenarios. It will give better performance. Plus there are delay constraints in high mobility scenarios, since UE will have to take account of time which needs to be used to compute this PMI value. So that's why in this specific scenario, low mobility scenarios, closed loop spatial multiplexing is the one which is usually used. Now let's talk about another cousin scenario for closed loop spatial multiplexing, which is open loop spatial multiplexing. Open loop spatial multiplexing is similar to closed loop spatial multiplexing. The only difference is in this case UEs are only going to report CQI value to the eNodeB and then rank indicator. That's it. UE is not going to send any PMI value back to the eNodeB. So that means in this case UE does not have to go through the long computation of calculating a PMI value and recommending it back towards the eNodeB. No PMI value being sent. That's why I put a cross here. So based on this scenario, open loop spatial multiplexing is being used in case of high mobility scenarios. And in this case, since UE can keep track of that computations, and eNodeB is the one which is going to compute PMI value on its own estimation, and it is going to use that PMI value during pre-coding. So that's the idea. In case of closed loop spatial multiplexing, eNodeB is also computing PMI value while UE is also sending PMI value. So both two PMA values will be received by the eNodeB. It's up to eNodeB's decision which particular PMA value it will use specifically in case of closed loop spatial multiplexing, while in case of open loop spatial multiplexing, eNodeB will compute it on its own and it will make its decision. So having said that, that was the brief understanding we need to have. Now we will go and take a look at a couple of slides how different scenarios take place in case of multi-antenna schemes. Before we go and do that, let's take a look at some of the scenarios. Though we started this discussion with this idea of multiple input, multiple output, however, there are different flavors of multi-antenna schemes. In some cases it could be multiple input, single output. In some cases it could be single input, multiple output. In some cases it could be both single input, single output SISO, which is without MIMO case. And all those scenarios are shown on this specific screen. As you can see, this is MIMO, this is SIMO, this is MISO, multiple input, single output. This is single input, single output. And similarly, you can have MIMO with a scenario like 4x2. So whenever you see any specific number like this, the first number represents what are the number of transmitters, and the second number represents what are the number of receivers. So in this case there are 2 receivers, okay, in this case there are 2 transmitters, and in this case there are 4 receivers. So that's the MIMO with unequal number of transmitter and receiver ports. Now having said that, we need to understand the concept of code word. Now you guys are familiar with the protocol stack of RAN side. When packet comes in from backhaul or from PDC player all the way down to RLC and MAC layer, we will talk about code word concept. I already discussed about this transmit diversity, beamforming and spatial multiplexing. This diagram is a repetition, in fact an enhancement or emphasis on what we discussed. We discussed already on the screen how transmit diversity can be used to improve the signal coverage and avoid or improve fading loss. And we can use beamforming to emphasize signal strength on one of the user or receiver, and then spatial multiplexing is used to improve throughput as it is evident from the screen. Again, another enhancement or emphasis on what we have discussed so far. If the UE is in good coverage, it can have more streams of information, as you can see over here using spatial multiplexing scenario. If UE is at the edge of the cell, we can go for beamforming, or we can go for transmit diversity, because when UE is at the edge of the cell, there will be more fading, noise and interference. So in that case, in order to improve reliability of transmission of the signal, we can go for transmit diversity in this case. Now, since we discussed a number of scenarios which can happen with multiple input, multi-antenna schemes, or multiple input, multiple output scenarios, based on those different scenarios in 3GPP standards, there are 9 different transmission modes defined specifically for the case of transmission being received on PDSCA channel. And those 9 different transmission modes you can see over here are listed. Each of the mode has a different control information format which is being received. And then it also shows the search space on PDCCH. What is the search space which is available in this specific scenario or case, and what will be the feedback from the UE in this case. As I mentioned already, you can take a look here. I mentioned in case of closed loop spatial multiplexing, we have CQI rank indicator PMA value given as feedback from the UE, while in open loop spatial multiplexing we only have CQ and rank indicator. So all these 9 different transmission modes are there depending on different particular combinations or schemes based on MISO, SISO, SIMO and MIMO scenarios it can happen. And this is as it is in the standard, and you can have an idea now what different scenarios it can occur into. So that was about MIMO. Now we are going to go through a number of scenarios how different code words are mapped onto the actual resource grid. Before we go into the code word, if you are wondering what is a code word, so I have drawn this protocol stack, which is the protocol stack on the eNodeB. When packets come all the way from backhaul to PDCP, those packets are sent down to RLC layer. Between RLC and MAC layer, we have logical channels which identify the type of traffic. And then after that, MAC is where the scheduler is. MAC layer is going to send it to transport channels so that the packets can be processed. By the time packet is received by the transport channels, it is called as transport block, right? And after the transport channels process the packet, by the time the actual information or the content of information comes out of transport channel, it is termed as code word. So the concept of code word is we are referring to this code word which has already been processed by all the protocol layers. They have already done massage and processing on that content or piece of information, and we are referring to this code word over here. And this code word you will see in a number of slides. So keep this thing in mind. This is what is being referred here. And this code word is actually, after doing pre-coding, etc. procedures, is mapped on the actual resource grid, which we are going to take a look in the coming slides. So get your understanding clear on this code word. Also, another important thing, we are only given 2 code words. Either you're using 4x4 MIMO, 2x2 MIMO. There always will be processing of 2 code words which will be mapped onto the resource grid, onto the physical channels. Having said that, let's take an example. If you have a code word coming in from the transport channels and it is coming onto the physical channels, how that code word will be processed? First, it's modulated, and depending on how many layers of information is available, layer mapping will take place. After layer mapping, pre-coding will take place. We talked about pre-coding earlier. In this case, based on the specific pre-coding matrix indicator, after pre-coding it will be mapped onto the resource grid, and after resource grid mapping we are going to go for OFDM signal generation. And once OFDM signal generation, your signal after D to A conversion, it will be transmitted into over the air or through RF amplifier.